Good morning. You excited to be here for RubyConf? Excellent, excellent. I'm glad to be here too. We are going to be talking about the Y-Combinator this morning. How many people here are very familiar with the Y-Combinator? Just a very few people. Very good. That means I can say anything I want to about it. I've got extensive speaking experience, and I've learned a couple rules, particularly about keynote talks. I mean, keynotes are just a little bit different than your regular everyday session. For one thing, keynotes tend to be a little less technical. You want to inspire the folks that are attending. You want to motivate them, so you tend to stay away from the highly technical talks. I am glad to say this morning this talk will be highly technical. Well, if you're going to be really technical, then maybe you should at least make what you're talking about relevant to the day-to-day life of the programmers there, so they can take home something that they can use in their, in their work. Use it tomorrow. I am glad to say that this talk is extremely pointless, and there's very little in this that you can take home and use. Well, if you're not going to be relevant, and you're going to be highly technical, then at least if you're doing code examples, make it examples of good code, good coding practices, so you're instilling those good practices in the people so that when they get home, at least they've got something out of that. I am also happy to say this will be the worst Ruby code you've probably ever seen. So what are the redeeming factors of this talk? Well, all I can say, it's going to be a little bit of fun. The first thing I need to do is I'm going to need a little bit of audience participation. So I need someone who has a calculator that can calculate the cosine of an angle in radians. Do I have any people who might have a calculator to do that? Anybody, any volunteers here? Oh, it's way in the back there. Okay, yes. Okay, you got a calculator in there? Go ahead and pull it out. Oh, good. He's coming up here. Excellent. Okay. All right, I want you to type in the number 0. Yep. Make sure you are in radians mode for cosine. Okay, and then hit the cosine button. Yep. Okay, you got an answer? I do. Okay, hit the cosine button again. Okay, hit it again. Hit it again. Keep doing that till I get back to you. Okay, the topic of my talk is called effectively computable. That's what we're going to be talking about. And this was a topic that was explored by a fellow named Alan Turing. You may have heard of Turing. He invented something called a Turing Machine. Now, a Turing machine is a simple machine that has an infinite tape with cells on it. Those cells, you can write characters into those cells, and you can then read back the cell, you can erase the cell and write a new character into it, and you can move the tape one position at a time, and all those functions are controlled by a very, very, very simple-minded program that sits and can say, if the current cell is a 1, then shift left and go to this, so very, very simple-minded programming. In fact, here is a animation of a Turing machine. I so want one of these devices. So if you're watching here, there is a camera here with a light, and you can see it's reading these characters right there. It's reading the 1, it's reading that 1. There's an eraser head over here that he can erase that 1 and then write a 0 in place of it. This is a counter. He initialized it with the number 11, and now we're up to 12. Now we're up to 13. And it's a very simple program that just reads the character under the camera and decides whether to change it to a 1 or a 0 and carries the 1 over. And it's doing binary counting. So we are up to, what? That looks like 14 now. Now we're up to 15. And now we're carrying the 1 all the way up. Erases the 1. Yeah, now it's running real time. It was actually running in fast speed before. This is real time now. Sees a 0, reads a 0. Reads the 1, erases it, writes in the 0. It's going to carry the 1, so it reads over until it finds a blank space, and then it carries the 1 over into the blank space, and the program's done. That is a Turing machine. Can somebody build me one of those? That's awesome. Turing said that anything that is effectively computable can be computed by this really dirt simple machine, this Turing machine. And what he meant by anything that can be computed, he's generally talking about mathematical functions or logic problems or things like that. Anything that you can write an algorithm to do, you can write that algorithm in a Turing machine and have your Turing machine calculate it out. That's kind of mind-boggling. And look at the date of this. This is in the 1936, 1937 time frame. The very first programmable computer was probably invented in Germany in around 1936. So he's doing all this research in his head, on paper. There's no computers that he's using to do any of this stuff with at all. So this is actually pre-computer work that's being done. Around the same time frame, there's this fellow named Alonzo Church. And Church designed something called Lambda Calculus. You might have heard of that. Lambda Calculus is a way of calculating things. It consists of the lambda character here, which introduces a function. After the lambda character will become a variable name, here x. After the x is a dot that separates the variable name from the body of the function. And in this case, the body of the function is another x. So this is, in essence, the identity function. You pass this function in any value, and it will return that very same value. So this is a very, very, very simple function in lambda calculus. This is all there is to lambda calculus. So there are no strings. There are no integers. There are no floating point numbers in lambda calculus. There are only functions and the calling of those functions. So how do we represent interesting things in it? Well, here's one particular scheme you might use to represent some numbers. Let's look at the number 1 over there. And you see it's a lambda function that takes an argument f, and it returns a lambda function that takes an argument x. In essence, you can think of this kind of, in my mind, I kind of group this together as a single function taking 2 arguments. And it takes the function f and applies it. It calls it on given the value x. So it calls the function f passing in an x one time. And that represents the number 1. The number 2 is represented by a 2-argument function that takes the function f and a value x, and it calls the function f twice on the function f. So that represents a 2. 0 calls the function f 0 times on the value. And this is how we represent number. We can represent any number you want to just by applying the function f multiple times to that value. And this is called a Church numeral. This is how you represent numbers in lambda calculus. How might you represent true and false? At the bottom of the screen, you can see true is a function of 2 variables, and true returns the first variable. False is also a function of 2 variables. It returns a second argument to that. So true is kind of like an if-then-else that returns the then part, and the false is an if-then-else that returns the false part. So that's how you represent true and false in lambda calculus. So keys to lambda calculus are that functions are the only data type. No integers, no strings, no floating point, no arrays, nothing else but functions. Lambda binding is the only way you can associate a value with a variable name. And you do lambda binding by calling the function on a value, and that will bind the value to the variable, the argument in the function, and then you expand the body of the function using that substitution. And all calculation in lambda calculus happens by a process called beta reduction. There's also another process called alpha reduction, but that's not the important one is the beta reduction. Let's give you an example of beta reduction. Here we have the lambda calculus representations of true, and it's being called on the number 1, and then the result of that is being passed in the number 0, and we're passing in the Lambda Calculus versions. So to do a beta reduction, you take the function in question, you identify the variable x, and you expand the body of the function out, and then you replace anywhere in the body where there is an x, the variable, you replace that with the argument. So the argument 1 gets substituted in for the x, and this is the final result of that beta expansion. Let's do one more beta expansion, expanding the result of this with the argument 0. So we identify the argument of the function as y. We expand the body of the function out, and we brought it down below. That's the red circle there. And then we substitute in 0 for the value y in the body, and it happens to be no value y in the body. So we're done. That's it. So if you pass true a 1 and a 0, it's going to return a 1. That makes sense. True is a function that returns the first argument. So that's beta reduction in Lambda Calculus. And you can see that Lambda Calculus is nothing more than macro expansion. It's merely text substitution that you take the arguments and you substitute them in and expand them out. This is really, really simple macro expansion here. Church said anything that can be effectively computable can be computed via Lambda Calculus. And I hope you're kind of scratching your head here, because I just said Lambda Calculus is nothing more than just simple macro expansion. But Church actually made his thesis. He beat Turing to the punch. He said this in around 1933, 1935. He wrote a couple papers on this topic. So he beat Turing by a couple years. In fact, when Turing's paper came out, and Turing said, a Turing machine can calculate anything that's effectively computable, there was a long debate in the mathematical circles whether the two sets of things that were effectively computable were actually the same thing or not. And generally today, we agree that Lambda Calculus and Turing machines, and then there was a third thing called general recursion that was also done. All of those things are Turing complete. In other words, they can all calculate everything that can be calculated in any of those three systems: Lambda Calculus, general recursion, or in Turing machines. Now, we see the influences of Lambda Calculus today. If you look at our language, Lisp has lambdas all over it. Clojure has an fn anonymous function that is essentially a lambda. In Ruby, we like lambdas so much we have several ways of doing them. CoffeeScript has a very concise way of representing lambdas, and JavaScript itself has lambdas as well. Anonymous functions are nothing more than lambdas or closures. If you went to Pat's talk yesterday on Block, you learned what a closure was. And this is all these things are closures or lambdas. Okay, so let's put that aside and remember that even though it seems hard for us to believe, Lambda Calculus is Turing complete, and there's a problem with that we'll get to in a little bit. But first, I want to return to the topic. Where's my volunteer?
Back here.
Oh, okay. What number did you get after pressing cosine many, many times?
0.739085.
Very good. Now, why do you? Thank you very much. I really appreciate that. Turns out, if you take the cosine of 0, that's a 1. If you take the cosine of 1, that is about 0.54, blah, blah, blah. And if you keep doing that over and over and over again, and if you do that about 89 or 90 times, kind of depends on how precise your floating point math is, you'll start zeroing in on a number that is 0.7390851, blah, 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 blah. This is a fixed point of cosine. That means if I give that 7 or that 0.73 number to the cosine function in radians, it will return that exact same number, and we have converged on this. So a fixed point is nothing more than a value you give to a function, and if that function returns the same value, then that is a fixed point. Turns out lots of functions have fixed points. Okay, here's the formal definition of fixed point, so you can see it. Give x to a function, it returns x. X will be a fixed point of that function. For cosine, cosine's a fun fixed point because you get to zero in on it just by hitting that cosine button a lot. But other functions have actually much simpler fixed points. For example, sine has a fixed point of 0. Cosine of 0 is 0. So, very simple. Square root, turns out it has 2 fixed points. Square root of 0 is 0, and the square root of 1 is 1, so both 0 and 1 will be fixed points of the function square root. If you had an identity function, any value you gave to an identity function would be a fixed point for the identity function. So there's an infinite number of fixed points for that function. And there's certainly some functions that have no fixed points at all. Okay, so keep the idea of a fixed point in your head. We're going to return to that. And we're going to switch now to the live coding part of the demonstration. Okay, very good. I'm going to, you guys are familiar with the stabby procs in Ruby 1.9, right? And you call them by saying dot parentheses. That's at least one way to call them. I'm going to put this into my code base right here, so I can just type in something, and the last thing in this list of expressions, when I evaluate the buffer, will just return the last thing in that expression right there. So that's just going to be a convenient way for me to evaluate a buffer and print things out. So let's talk about the problem with lambda calculus, and I'm going to demonstrate it by writing a factorial function. And we'll use the stabby proc notation. So factorial is a function of one argument. If that argument is 0, then the answer, the result of factorial on 0 should be 1. If it's not 0, the result of factorial should be n times the factorial of n minus 1. And I can prove that works by calling factorial on 5, and we know the factorial of 5 is 120. Very good. And indeed, that's what we get. All right. But in lambda calculus, I'm not really allowed to assign things like this. I have to create a lambda expression and then call it directly. So I'm going to try to call my factorial problem like this, and it says, oh, I don't have a method called fact defined anywhere. And that's because I'm using fact in the definition of the function I'm defining. Well, in lambda calculus, all functions are anonymous. So how in the world can I define that factorial without referring to itself? And that's a problem. So how can lambda calculus possibly be Turing complete? I'm going to leave that comment up there and just think about that for a while. And there's about 3 or 4 topics I want to cover first before we go back and solve this problem. The first thing we've already talked about. The first thing is fixed points. So you guys know what a fixed point is. It's a value when given to a function, the function returns that same value again. The next thing I want to do is talk about higher order functions. Now, how many people here are familiar with higher order functions? Yeah, I suspect most of us are. The rest of us who are not probably use them all the time and don't really realize that in Ruby. Each, in its own sense, is a higher order function. Let's talk about regular functions first. I'm going to write a function called add1 that takes a number and adds 1 to it. And I can demonstrate that add1 works by giving it a 10, and I should get an 11 out of that. So add1 is a very simple function. Let's do another simple function just for demo purposes. It's going to be multiply by 3. We'll take n and multiply it by 3, and we'll multiply by 3 the result of adding 1 to 10, and we should get 33 out of that. So add1 and mul3 are both basic simple functions. They take a value, they return a value. Let's write a higher order function now. Oops. MakeAdder is a function that takes an argument x, and what it's going to return is another function that takes an argument n that adds x and n together. So MakeAdder is a function that creates a new function. Given the x, it will take that x and it'll create a new function that will add x to anything that you give to the new x. So I could actually have rewritten add1 like this, MakeAdder 1. And that's a decent definition of add1. And we can evaluate our buffer and see we get the 33 back, so add1 obviously must be working. So MakeAdder is a higher order function. It's higher order because its return value is a function itself. That's all it means to be a higher order function. It returns functional values. Here's another higher order function. We'll call it compose. Compose takes functions as arguments. two functions in this case, f and g. It's also going to return a function. It's going to compose f on top of g called on n, and return a new function that calls f and g on top of each other. We can now create a function called mul3 add 1 that is the composition of mul3 and add 1. And then we can use that newly composed method right here, and we see we get the same answer, 33, back. Compose is a higher order function. It's higher order for two reasons. It returns a function, but it also takes functions as arguments, and that's enough to make it a higher order function as well. We are going to use higher order functions a lot in the rest of this demo. So if you've never seen them before, just get comfortable with the fact that functions are values and we can manipulate them just like we can manipulate strings and integers and whatnot. All right, higher order functions. Next topic will be functional refactorings. And just like in the object-oriented world, there are refactorings that we can do, like extract method or collapse hierarchy. There are a number of refactorings that you can do in the functional world as well, and they are purely functional in flavor. The first one I want to talk about is the tenant correspondence principle. Okay, tenant says if I have an expression x and I surround it by a lambda and then immediately call that lambda, I get x back. It essentially has no effect. It's a true refactoring in that it does not affect the code. So let's demonstrate that. Let's go down here to mul3, and inside mul3, I'm going to wrap this expression inside a lambda, and then immediately call the lambda. That's the tenant principle. And we see that it has no effect on the outcome. We still get 33. It is a true refactoring. Let's do it one more time. I'm going to wrap this whole functional expression in a tenant lambda. And this time I'm going to do it with an editor macro just to show that these things truly are mechanical. There, my editor did it for me. And yes, we get 33 out of it. So the tenant principle, very useful in functional refactoring. Our next refactoring will be to introduce a binding. So if I have a lambda here with no arguments, I can add a new argument binding to it. We'll call it z. And then if I add an argument here, when I call it, I have to give it a value. And I can give it any value that I feel like. Because z is not used anywhere, it doesn't matter what value it takes. So I can introduce the argument z and evaluate that, and it's still 33, no effect. Now there's one rule you have to follow, and let's demonstrate that here. You have to make sure that any variable you add in that you introduce is not free in the expression you're wrapping. So down in here, we've got variable n. N is not free because it's bound right here. So I could actually reuse n. It'd be confusing, but I could. But f and g are both free variables in this expression. They're defined outside. So if I were to take f in here and give it an arbitrary value, it would die. Whereas if I called it n, that would work. Generally, I'm going to avoid using any used variable at all. So x, y, z, z, y is a good choice there, and that works. But as long as you stay away from free variables in the expression you're wrapping, it doesn't matter what the variable name is. Number 3 will be wrap function. If I have an expression that is a function of one argument, I can wrap that in a lambda of one argument and then call the function inside that lambda and pass the argument down to the call site. Let's demonstrate. Here is a function of one argument. I can wrap it in a brand new lambda with an argument of v. There it's wrapped. Then on the inner function that I just wrapped, I need to call it immediately and pass v in. This essentially What I'm doing is makeAttr now returns a lambda that has the same signature as the function it was previously returning, but it doesn't actually evaluate the lambda on the inside until you call it again. So it's kind of like a delaying tactic. If you don't want to evaluate something right away, this is something you can do to do that. And you can tell, I still get 33 out of the result. So function wrapping is a true refactoring. One final one. You'll love this one. This is inline definition. I can take any definition here, in this case the definition of makeAttr, and wherever makeAttr is called by name, I can replace the name of makeAttr with the definition. And let's delete this line here. And when I evaluate that, same result. Again, this is totally mechanical. I can take compose and run the inline refactoring on that. Say yes, replace that. I get the same result back. Oh, let's go wild with this one. Inline add one. No, that's part of the name, but here's add one, yes. Let's inline mul3. There. Okay. One more time, guys. Let's inline this guy. Oops. I did promise you the worst Ruby code you'd ever see, right? That mess, let's evaluate it, still returns 33. Now, the really interesting thing about this is a pure lambda expression. There are no assignments anywhere in this. The only binding that we do to variable names is through calling these lambda functions. And we do a lot of calling of the lambda functions. And that's really ugly and very unreadable, and I don't recommend writing code like this, but it proves a very important principle that lambda calculus, this is the goal of what we want to get to in lambda calculus, is to have one big lambda expression that does this calculation. Okay, enough of the preliminaries. Seems a shame to write all that and just delete it, doesn't it? Let's get back to the problem of recursion. And let me grab my factorial thing and let's paste it back here and uncomment. So this is what we're dealing with. I want to write a factorial function that's recursive, and I can't because I cannot refer to factorial inside the definition of factorial because there are no names for these functions. Well, I could actually. There are names, they're introduced by lambda binding, so I actually could do this. I could say, let's create a function that has factorial as an argument. And then now factorial will be bound to this, and let's call this make factorial, okay? And then all I have to do to create the factorial function is to call make factorial, and all I need to do is pass in the definition of factorial. Now think about that for just a sec. Okay, I haven't solved the problem yet. I've just made it a little, I've just introduced some indirection there. Okay, so that's not going to work because to make a factorial, I need the definition of factorial. A little bit circular logic there. I need to do something else. Well, okay, maybe I can relax the requirements a little bit. Maybe I don't need a make factorial. Maybe I need a function that is a factorial improver. And instead of taking the definition of factorial as an argument, it will take a partial definition of factorial as an argument. And by partial, I mean a function that acts like factorial over a subset of the possible inputs. In other words, if I have a factorial function that works from 0 to 10, it can calculate the factorial of 0, 1, 2, 3, on up to the factorial of 10. If I pass that partial definition of factorial into my fact improver, I will get out of that a new function that works for factorial from 0 to 11. It improves any factorial definition by one step. That's kind of cool. So I need an error function here, so bear with me while I write this. Okay. This is just a function of one argument that throws an error so we can see what's happening. Now, if I factorial improver, and I call that on error, I claim I will get out of this a function I'll call f0, because f0 correctly calculates the factorial of 0. Oops. Oh, I left this 5 on there. That 5 should not be in there. Yes, it correctly calculates the factorial of 0. All right. Well, that's interesting. Oh, but if I can calculate the factorial of 0, I can create a function that calculates the factorial of 1. Yeah, but f1 does not calculate the factorial of 2. Oh, but if I got one that calculates 1, I can write an f2 based on f1 that works for 2. Does it work for 3? No, not at all. Okay, you can kind of see where I'm going with this, maybe? Before I go any farther, let's inline some of these things. So I'm going to do the inline refactoring there and there. Okay, and let's call this fx right now, not tie it to a particular number. And then I'm going to take this from here to here. I'm going to cut it and paste it 1, 2, 3, 4, 5 times. 1, 2, 3, 4, 5 to balance the parentheses. And now fx calculates the factorial of 5. It'll do 10. It'll do 14. But it will not do 15. Well, I'm getting closer to my goal. All I have to do is decide the biggest number I will ever want the factorial of and call fact improver on it that many times. Okay, maybe that's not quite so practical. That's not going to get us to the real factorial function. Okay, let's get rid of that. Let's think about this. Well, first, before I go any farther, let's go ahead and do the whole embed this in a lambda trick. So I'm going to create a lambda function that expects a factorial improver as an argument. And here's the body of that function. Oops. It should be open parentheses and close parentheses. So here is the body of the function. Here is where I'm passing in the argument. I'm passing in the factorial improver. Let's just call it improver for right now. And then in here, I can do the same tricks I was doing elsewhere. I can say improver.error. And if I put this into fx, then fx should work for 1, but it won't work for 2. Nope. Okay, so this is exactly the same thing I did before, except I've embedded it in a lambda and binding the improver. Instead of assigning to improver, I'm binding to it with lambda binding, which is what we want to get to anyways. Improver is interesting. Improver says I can take any function and improve it by one step. I was using this error thing, which obviously has nothing to do with factorial at all, but I'm wondering if I replaced error with just improver, I should get a function that works for factorial of 0. It does. But if I call factorial of 1, it should fail in a weird way. And the weird way is that it says that proc can't be coerced to a fixed num. And the error happens right here on this line, right at this multiply, where it's taking n times that. And this partial now is the improver function, and improvers expect functions, not numbers, so of course this is not working at all. In fact, we can make this very much plainer if I replace the word partial with improver here. Since I'm, oops, sorry about that. Back down here. Since I'm passing in improver to improver, and this is improver, so let's call it improver as the argument. I'm actually doing that. And this becomes very plain that improver does not take a numeric argument. Improver expects a function. Oh, I've got a function laying around. Let's pass it improver. Gosh, I wonder if this could possibly work. Well, factorial of 1 is good. How about factorial of 2? Oh, how about 5? Oh, how about 50? How about 500? I think I can go up to 2,000 before I overflow my stack, yeah. So there, factorial of 2,000. Yep. And here you go. Here is, let's make this all the way pure lambda calculus by defining the function and then calling it with the argument 5 at the end here, and we will have a pure lambda expression that calculates factorial. Now this is good enough for our goal of proving that lambda calculus can actually calculate arbitrary mathematical functions. Recursion is no problem for it. By doing this little trick of passing these things to itself, it actually can do recursion with lambda calculus, even though lambda calculus is nothing but anonymous functions. This is mind-blowing to me, actually. But I'm still not quite happy with this definition here. There's two things I don't like about it. First of all, I'm calling this thing improver, and it's no longer improver. Improver took a partial definition. This function is taking something that is not a partial definition. So this thing here should not be called improver at all. It should be called something else. So let's replace the name improver with a different name, and here I get stuck because I have no common name for the thing that this argument now is. It's no longer an improver function. I'm going to go with the name gen because it's a generator that somehow when you feed it itself, when it swallows itself, it generates a recursive function. If we can live with that, that's what I'm going to call it for the purposes of this demonstration. And I can see that I haven't changed anything. We still have a working factorial system there. So that's the number one thing I didn't like. The second thing is that if I were to sit down and write a recursive function, it would never in my entire life occur to me to write it in this manner. There's lots of mechanics right here involved in just to do the recursion. And I want to be, if I could get this in a form where I was writing factorial as an improver function makes a lot of sense to me. That seems more or less natural, at least in the lambda calculus world. If I could get back to the improver form of this, I would be really glad. So let's see if we can work on this code base just a little bit. I'm going to take this inner lambda right here, and I'm going to do the tenant correspondence principle refactoring on it. There we go. Let's break that up just a little bit here. So I wrapped this in a lambda and immediately called the lambda, and it has no effect. It does the same thing. So we still have a working factorial, didn't break anything. Now I'm going to introduce a binding. And the variable name I'm going to use is code. That's the name of the variable. And the value I'm going to pass in will be my error function. Because remember, when you introduce a variable, introduce a binding, the value doesn't matter. It can be anything. So there I have a function that takes an argument of code, and I'm passing in the error function. And we're not using code anywhere, so we never trigger the error, and it still returns 120 for the factorial 5. Okay. Well, I can pass anything in. Let's pass in gen. Hey, that still works too. Oh, you know what? This whole gen of gen thing is actually as a function. Let's call gen of gen. And oops. Stack too deep. This is what has happened. I'm calling gen of gen inside of here. And so this entire thing, let me mark this. This entire thing right here is the gen function. So when I call gen and pass in gen, it goes and it would call gen of gen inside of here, but it only called it if n was not 0. So it actually bottomed out. It would actually terminate. Here I'm passing in gen of gen, and it always calls gen of gen, even when n is 0. So it has infinite recursive depth in there, and that's no good. Oh, if there only some way of delaying evaluation. Let's wrap it in a function. Here's my wrap function. Argument name will be v. So there I've taken gen of gen and replaced it with a lambda, so when I call it, it doesn't infinitely recurse, it just passes the lambda in its place that is functionally equivalent to calling gen of gen. And we see this actually works. Okay, next step. I've got code. Code is bound to that lambda that evaluates the gen of gen. And we know that here, let's go ahead and wrap this as well. And I see right here, from here to here, this is the exact same thing that I'm passing in to code. So let's just call code instead. And that works. That's interesting. Let's rename code to partial. And all of a sudden, out of nowhere, that little piece of code right there is our improver function. And we've got it back. Cool. But it's still buried in the middle of all this recursive stuff. Let's see if we can pull it out. So out here, from here down to here, not including the argument call, but the entire body of the function, I'm going to do a tenant refactoring again. That wraps it in a lambda. Let's put some line feeds in and pretty up the indentation a little bit there. There we go. And I'm going to introduce a new binding here again. Introduce binding. And the binding will be code. The value will be error again, because that worked so well for us last time. And that still works. That's still 120. Okay. Now I'm going to point out that here is the improver. I'm going to copy the improver from here and call, pass in the improver as the value of code. And that still works because we're not using code. But I point out that code is now the same thing as the improver function embedded in here. I can replace this now with code, and it still is 120. And now let's rename code to be improver. Rename code to be improver. I was practicing this morning. I was typing improver so often, all of a sudden I started reading it as imp rover. And yeah, replace those two with improver, and we still got 120 out of that. And there we have a complete lambda expression. Here, this part of the code right here deals with the recursive nature of the problem. This piece right here is the only piece that knows anything about the definition of factorial. So this is really nice. This is exactly what I want. And now that I've got a complete lambda expression that does this, I'm going to pull the pieces out and name them so we can talk about them reasonably. So let's pull this out. I'm going to call this fact improver again, imp rover. And let's put it up here. Fact improver is that. Nice indentation. Still works, no problem. Let's take out this piece right here. I'm going to call this, I'm going to call this piece y. Get some nice indentation going on that. Oh, it's already, okay, very good. And then I'm going to take this out here, and I'm going to call this piece fact, or factorial. And then we'll call factorial right there. Everything still works. And I'm going to clean this code base up just a little bit here. Streamline it just a wee bit. Okay. And so now I got three pieces. Now let's start with the bottom and work our way up. so here's this is factorial. This is the real factorial function, and I prove it by calling factorial 5, and it actually does calculate the factorial of 5. If I were to take the factorial function and run it through the fact improver, what will come out of that? Well, fact improver takes a partial function and improves it by one step. But if I've already got the real factorial function, all improver can do is return the factorial function. This is indeed the factorial function. And I can run this, and I still get 120. So we're using this definition of factorial now, not this one. And so that proves that fact improver returns its argument. Factorial, let's write this down. Factorial is the fixed point of fact improver. I'm going to say improver now in my head every time I do that. Factorial is the fixed point of fact improver. Higher order functions have fixed points as well. Their fixed points happen to be functions, but that doesn't change the fact that they're fixed points. Well, that's interesting. Now, I'd like to point out that the function y calculates the fixed point of an improver function. In this case, we're calculating the fixed point of the fact improver, but I could write any recursive function I wanted to, and it would calculate the fixed point of that recursive function, as long as it's done in an improver style. I could write a Fibonacci improver, and it would work perfectly well. So y calculates that. So let's talk about y. So y here is actually the Y-Combinator that we've all heard about and loved. Well, maybe not loved. In particular, there's actually many versions of the Y-Combinator. And if you go to Wikipedia, you will not see this version at all. First of all, mathematicians don't like intention-revealing names. So they call improver F. Oops, too far. And they call the generator function, I've seen it called G, I've also seen it called X. The Wikipedia article uses X, so we will use that here. And so this is probably more likely the form of the Y-Combinator you'll see with variable names F and X in it. But we haven't changed anything. We're still calculating factorial. The other issue here is this in particular is the applicative order Y-Combinator. Ruby is an applicative language. In other words, it evaluates its arguments before it passes the arguments down into functions. Ruby is applicative, Python is applicative, Lisp and Clojure are all applicative languages. Examples of languages that are not applicative would be Haskell. Haskell is lazy. It will evaluate its arguments only at the point it really needs them. So there is a version of the Y-Combinator for normal order languages like Haskell, and the difference is that you don't have to introduce this wrap function thing right here that we had to do to prevent our infinite stack recursion. So that would be the normal order Y-Combinator. And when you talk about Y-Combinators, normally they mean the normal order in the mathematical sense. In a language like Ruby, we need to use the applicative order version instead. The applicative order has another name. It's called the Z-Combinator. Why these things have so many names, I have no idea. It's also known as the fixed point combinator, because it is the combinator that calculates fixed points of functions. So there you have it. One more thing. If you go to the Wikipedia page, you will not find it in exactly this format. There's a preferred style they like to write it. And I'll show you that through two refactorings here. Remember, f is really the name of the improver function. So if I call f on this x of x thing, I'm just improving the factorial function, and that is a no-op in this term. So this still returns 120, no change. And then I can also do a function wrap here. And we know function wrap doesn't change anything, and we can see it doesn't. And then if I take off 2 levels of indentation, all of a sudden you see a great symmetry between the body of the function and the argument you're passing in. And this is the version you will probably see if you look it up in Wikipedia or some math on computational science. So there you have it. There is the Y-Combinator derived from first principles. Wow, my brain is dead after that one. I started on this journey because I always heard about the Y-Combinator, and I really wanted to understand it. Now, people will ask, oh, that's cool. Well, how can I use the Y-Combinator in my own code? Well, if you have named functions, you don't need the Y-Combinator. If you want to write all your code as anonymous functions, then maybe the Y-Combinator would be useful, but I don't really recommend that. What I found interesting, though, is that by starting with some very basic principles and applying these refactorings, I found the functional refactorings to be very fascinating. And that by applying that, you could take something in one shape and transform it and get it into a different shape that's more appropriate for the needs that you have. I really enjoyed playing around with those refactorings in that exercise. So now you can go home and you can explain to all your coworkers that you have you've seen the Y-Combinator, you understand how it's done. I think the Y-Combinator is one of those examples of great beauty in mathematics. It's a really interesting function that is theoretical in a lot of respects, but comes out of something like Lambda Calculus, which seems trivial, a trivial macro replacement type of language, but yet Lambda Calculus is buried so deep into Ruby, we use it all the time without even realizing it. It's one of those things that have a great and profound impact. And that's one of the things I really enjoyed researching this particular topic, and I hope you guys enjoyed it as well. If you liked this, I'm going to recommend a talk called Programming with Nothing by Tom Stewart. Tom uses nothing but lambdas, the stabby procs, and calling thereof, and writes the FizzBuzz application. He uses no integers, no strings, no logic of anything except calling lambda functions. It's a true example of Lambda Calculus done in Ruby. And that's a fun, just Google Programming with Nothing and you'll turn up that video. I recommend that one. So thank you very much. You guys have a good day.